Time travel. It's the ultimate science fiction dream, isn't it? The power to witness history firsthand or to glimpse the wonders of the future. For decades, it's been the stuff of movies and novels, a fantasy we've all entertained. But what if I told you that, according to the fundamental laws of physics, it's not entirely fiction? The headlines might scream that it's just around the corner. But before you start packing your bags for a trip back to the 80s, let's separate the science from the fiction and see what the universe actually allows. The journey begins over a century ago, with one of the greatest minds in history. In 1905, Albert Einstein turned our understanding of reality on its head with his theory of special relativity. He revealed that space and time are not separate and absolute, but are woven together into a single fabric, space-time. And this fabric can be stretched and squeezed. The key insight? The faster you move through space, the slower you move through time. This isn't a guess. It's a proven phenomenon called time dilation. Imagine you took a trip on a spaceship traveling at 99.9% the speed of light. For you, a year might pass, but when you return to Earth, you'd find that decades or even centuries have gone by. In a very real sense, you would have traveled into the future. This isn't just theory. We see it in action every day. The GPS satellites orbiting Earth move faster than we do, and their internal clocks run slightly slower. If our systems didn't correct for this tiny relativistic effect, your GPS would become inaccurate by several miles every single day. But speed isn't the only thing that can warp time. Einstein wasn't finished. His theory of general relativity showed that gravity is a curvature of space-time caused by mass. The more massive an object, the deeper the gravity well it creates, and the slower time passes nearby. This effect is minuscule for planets like Earth, but it becomes extreme near incredibly dense objects like black holes. If you could hover safely near a black hole's event horizon, time for you would slow to a crawl compared to the rest of the universe. Hours for you could be millennia for everyone else. Again, this is a form of one-way travel to the future. So, traveling forward in time is scientifically plausible. But what about the past? That's where things get much, much stranger. General relativity also allows for some truly exotic solutions, like the possibility of wormholes. These are theoretical tunnels through space-time, cosmic shortcuts that could connect two distant points in space, or even two different points in time. Imagine folding a piece of paper in half and poking a pencil through it. That's the basic idea. One end of the wormhole could be here and now, and the other could be in the same location, but 100 years in the past. Sounds like the perfect time machine, right? Well, there's a catch, a very big one. According to our current understanding, any wormhole large enough for a person to traverse would be catastrophically unstable, collapsing in an instant. To keep it open, you'd need something called exotic matter, a hypothetical substance with negative energy density. Think of it as anti-gravity. We've never observed such matter, and we have no idea how to create it. The world of quantum mechanics offers its own mind-bending possibilities. Some interpretations of physics hint at the existence of closed time-like curves, or CTCs. These are paths through space-time that loop back on themselves, allowing an object to return to its own past. It's like walking in a straight line and ending up right where you started, but yesterday. While mathematically possible in some models, there's no evidence they exist in our universe, and they open a huge can of worms. This brings us to the infamous paradoxes. The most famous is the grandfather paradox. What if you travel back in time and prevent your grandparents from meeting? You would never have been born, so you couldn't have gone back in time to begin with. It's a logical contradiction that seems to forbid travel to the past. Physicists have proposed solutions. The Novikov self-consistency principle suggests that the laws of physics simply forbid any action that creates a paradox. The universe would conspire to ensure you can't change the past in a contradictory way. Another idea, from the many worlds interpretation of quantum mechanics, is that changing the past would simply create a new, parallel universe, leaving your original timeline untouched. So, where does that leave us? What's actually doable? As we've seen, traveling to the future is, in principle, a reality. Astronauts on the International Space Station age a few milliseconds slower than us on Earth over their 6-month missions. It's a tiny effect, but it's real, measurable time travel. To achieve more significant jumps into the future would require technology far beyond our grasp, either spaceships that can approach the speed of light or the ability to safely manipulate the gravity of black holes. The energy requirements alone are astronomical, and the engineering challenges are currently insurmountable. As for traveling to the past, the consensus among most physicists is that it's likely impossible. The hurdles, from needing undiscovered exotic matter to resolving universe-breaking paradoxes, are just too high. While the equations might allow for it on paper, the universe seems to have strong rules in place to protect causality. So, for now, don't cancel your plans for next week. Time travel remains a fascinating theory and a wonderful frontier for the imagination, but your weekend getaway to the Renaissance will have to wait. The past is for our history books, but the future? Well, we're all traveling into it together, 1 second at a time, and who knows what discoveries it holds.